this on? Okay. So good afternoon to you all, and thanks to the organizers for giving me the opportunity to talk here, and it's an honor to celebrate Professor Bala Iyer's life and work. So the previous two talks were about model independent tests of GR mostly, while in this talk I will talk about some model dependent tests and what are the generic features that arises out of it. So let us start by saying why one should look for theories beyond general relativity. There are several modifications thereof. I will just talk about a few of them. So the first comes from the consideration of symmetry in this theory. So constructing any Lagrangian, you often infer to symmetry principles, saying we should write down all the terms in the Lagrangian which are consistent with the symmetry. And in the case of GR, that corresponds to the general coordinate invariance of the Lagrangian. And in that context, we can add more terms over and above the Einstein-Hilbert term. For example, one often adds the Gauss-Bonnet term in 4 dimension with a scalar coupling to make it non-trivial in that direction. However, the most non-trivial motivation for discussing the theories beyond GR originally came from the late-time accelerated expansion of the universe. And in that context, in order to explain that thing, instead of introducing some exotic matter like dark energy, one often invokes some sort of higher curvature corrections to the Einstein-Hilbert action, or introduce some sort of a non-minimal coupling between scalar field in order to reproduce these theories. So that is also like in dark energy or modified gravity, whichever is your favorite choice. Then there are, of course, some other motivations, like, for example, people talk about appearance of space-time singularities in general relativity and incompatibility of general relativity with quantum theories, but till date we do not have any other higher curvature theories which solves these two problems. So this just remains at the level of motivation. But if we want to go for theories beyond general relativity, what should be the guiding principle that should take us? Because in general, we can add a large number of terms, and even if we say the Lagrangian should be diffeomorphism invariant, there would be an infinite number of terms in them. So one of the most important principles would be that the field equation should be second order in the dynamical variable, because often if the field equations are higher order in the dynamical variable, there are certain instabilities that come in, which are known as the Ostrogradsky instability. And this actually fixes a unique class of theories in particular Lagrangian. So one would be the Lovelock class of theories, like Einstein theory, Gauss-Bonnet theory, and so on. And the other class of theories would be scalar coupled Einstein gravity, which would be Galilean theory or Horndesk-Kiskorber theory. Or the other option would be for space-time to have more than 4 dimensions. That is, either they could be large or they could be compactified extra dimension. And as I mentioned, even though they appear completely different in their appearance, their implications on various GW observable will turn out to have some generic nature. So, and the resulting modifications are obviously that the field equations would be modified, like instead of having Einstein's equation, you will have some different set of equations. As a consequence, even though you may have the identical solutions, like Schwarzschild could be a solution to the modified theories, but the corresponding perturbations will evolve following a different evolution equation. And as a consequence, all the observable properties of gravitational waves will be different. So some implications or some scenarios or some observables that you may want to observe. So in the context of post-Newtonian formalism, the notion of tidal love numbers, which has already been discussed in Chris's talk, and universality relation, which I don't think has been discussed. I will talk about these two in turn. Then in the merger phase also, there would definitely be modifications, but as Chris has already mentioned, that there is no numerical relativity waveform available in the merger phase. Actually, there is no numerical relativity simulation for theories beyond GR, as far as I know, except for this paper by Chopwick, where they discuss some sort of a black hole collision and merger in an RS2 brane world model. Then, of course, there would be some modifications in the quasi-normal modes in the ring down phase of the signal. And of course, there would be effects on the polarization mode of the gravitational waves. So I will try to discuss them. There would, of course, be other modifications like in the multiple moments and so on. But for the time constraint, I will discuss only these few. So let us start by discussing the quasi-normal modes. So as Chris has mentioned, that the quasi-normal modes carry all the imprints or all the hairs of the black hole. So therefore, one can actually use it to test the null test or to test the no-hair theorems. So if one can detect the first few quasi-normal modes associated with the ring down phase, then it's actually possible to talk about what are the hairs associated and whether there are any deviations from general relativity. But that requires a high signal to noise ratio, which currently we do not have. So we are not in a position to talk about alternative theories of gravity right at the moment using the quasi-normal modes. But hopefully these difficulties will be overcome in the next generation detectors. And as I mentioned that in most of the alternative theories, there are also scalar coupling to gravity, and as a consequence, just like the gravitational quasi-normal modes would be modified, there would be additional quasi-normal modes in the problem, maybe a scalar quasi-normal mode or the vector quasi-normal modes. So that will lead to some additional polarization degrees of freedom. And if one wants to disentangle all possible polarization, one actually needs some 5 GW detectors which are non-aligned. And but we do not have it now, so possibly LIGO India will help us in that manner in future. But there are still certain constraints on the particular scalar modes or tensor modes because we have not seen them. On the other hand, there is some suggestion by this gentleman in this particular paper where they discuss that these additional polarization modes may only couple weakly to the GW detectors, and as a consequence, not seeing them may not be some facet of the corresponding scalar tensor theory. The other point that I just want to remark upon is that the quasi-normal modes in the eikonal limit or the geometric optics approximation is actually related to the instability of the photon sphere in the black hole. And we know that is the photon sphere which relates to the black hole shadow. So there could be some possible connection between the two, and whether one can use the black hole shadow technique to infer about QNMs, and there could be some relation between future GW observers. Yes.
Quick comment. I think you need 5 detectors only. You have a transient signal.
Yes. Yeah, that is correct. I mean,
you can repeat what I said.
Yeah. So he said that you need some 5 GW detectors for transient signals, but otherwise, yeah, you can do it continuous. You can do it small. Yeah, correct. Yes. Yes.
The CW thing, since you observe for a long time, it's like having many detectors. Yeah.
So just to give you an idea that how quasi-normal modes in different gravity theories may look like. So the plots on the top are for theories with extra dimension, while the plot on the bottom is taken from this particular paper, which is for another theory of gravity, which is called dynamical Chern-Simons theory. So as you can see that in the presence of blue one in both the cases essentially corresponds to the general relativity curve, while the red one here corresponds to prediction from brane world, and here the black and red, they both corresponds to some deviations from general relativity. So as we see in both of them, after maybe 2 or 3 cycles, it's actually the alternative gravity waveform, alternative gravity quasi-normal modes, they start to dominate. And the similar here, this one goes down while the black one starts to dominate. So the point is, if one can actually detect the quasi-normal modes to some high sufficiently late times, then one can actually see some signals of presence of higher curvature theories or any of these theories, and actually one can constrain them in certain epoch. Now I have just shown here just 2 of the plots, but in all the most of the other cases, like even for Einstein, Dilaton, Gauss-Bonnet, and the other alternative theories that we have, a very similar feature one can observe in the quasi-normal mode spectrum. It's sort of a generic feature that after a few GW, I mean the standard GR predictions, then the alternative theories dominate over because their decay rate is much smaller in most of the cases compared to the general relativity counterpart, and that provides a very nice opportunity to look for them in the future GW detectors. So the next probe that I want to talk about are the tidal love numbers. So this corresponds to the fact that if I have a compact object and it is moving in a binary, then due to the additional gravitational field, it will be deformed. So the external gravitational field as well as the deformation of the tidal object, they are both encoded in this proportionality parameter that we call as the tidal love number. Now the most important result in the context of GR is that if you consider a black hole in general relativity, then the tidal love number for that identically vanishes. But if you consider black holes in theories which are beyond general relativity, like maybe either the dynamical Chern-Simons theory or theories or black holes in higher dimensions, then that leads to a non-zero value for the tidal love number, and that can be a very nice test for theories beyond GR, that whether in a binary black hole merger you get a non-zero value of the tidal love number or you get a 0 value. The 0 value corresponds to the GR case, while a non-zero value corresponds to some theories beyond GR. The next one corresponds to the universality relation, which is the universal relation between the tidal love number, the moment of inertia of a neutron star, and the quadrupole moment of the neutron star. So originally, there was some degeneracy between them because people knew that for different equation of state, there could be different values of this quantity. But some work by Nicholas Yunes and Ken Tiagi showed that it's actually an equation of state independent relation, and it holds for all sorts of equation of state. It turns out there is also a universality relation between the tidal love number and the compactness, which is the mass over radius for the neutron star. So actually from the GW signal, if you know the tidal love number and the mass of the neutron star, you can infer about the radius of the neutron star using this universality relation. Now one often asks the question that what happens as you go for beyond GR, whether the universality breaks down, and if the universality breaks down, then that's a big problem because then you cannot predict without the degeneracy factor taken into account. But it turns out that in various other contexts, like in the case of brane world as well as dynamical Chern-Simons theory, the corresponding universality relation still holds. That is, the relation between the tidal love number, moment of inertia, and quadruple moment is still independent of the equation of state of the neutron star, but they differ from the corresponding relation in the context of general relativity. So therefore, you can still use this relation. So if you have a GW observation between two binary neutron star, the GR prediction for the radius would be different from the radius prediction from other theories of gravity because the corresponding universal relation would be different from that of GR. So just to show you how this comes about, so the plot on the first panel corresponds to a plot between moment of inertia and the tidal love number, while this corresponds to a plot between the compactness and the tidal love number. So this is for general relativity. So you can see that for various different equation of state, they actually follow a particular curve, which is sort of universal, independent of the equation of state. But as I introduce some additional parameters into the theory, the curve remains universal while it deviates from that in GR, even though by a small amount, but the universality relation still holds. And a very similar situation holds for the dynamical Chern-Simons theory, which was originally shown in their paper itself, and you can actually do it for other theories of gravity. So this is another way where you can actually look for deviations starting from GR. The next one is, of course, already discussed by Chris in his talk, but I just wanted to mention 2 or 3 more points. So in the case of black hole mimickers or in the case of echoes, there is very strong instability issues associated with them, which I think he did not mention. So for example, in the case of the exotic matter distribution, like the case of boson star, there is a very strong ergo region instability which appears. And therefore, most of the, this exotic matter contribution are unstable in the large rotation limit, and therefore they have an apparent time scale, lifetime of the order of 1 second. So therefore, that makes them not so much suitable for rotating objects. Secondly, he talked about fuzzball-like structure. So there was some work by Harvey Rial and his collaborators which actually showed that the fuzzball-like structure can have some stable trap geodesics, and as a consequence, the quasi-normal modes associated with them will decay very slowly, which will lead to some nonlinear instability in these theories. So except for wormhole-like geometries, which can have some stability issue, all the other possibilities apparently, till date, seems to have incurred these instability issues. I think one needs to talk about this instability before going into discussing the GW observation possibility. So this also he discussed, so I will not go into this thing. I will go to another arena where one can look for, which is the modified dispersion relations. So the violation of local Lorentz symmetry, that will also lead to modification because the propagation speed of the GW will be affected. And the future GW measurements can actually provide some stringent bound on these 2 particular theories, the Einstein-Aether theory, as well as the Horava-Lipschitz gravity. So the Horava-Lipschitz gravity was discussed in this paper in light of the recent GW measurement, and the paper by Arun and Yuns, they actually discuss what happens to the future GW detectors in connection to these particular theories and also others. Similarly, massive gravity theories will also modify dispersion relations, and they will also lead to certain interesting constraints. So just to give you an idea that how GW can actually rule out several of these models, so just one particular binary neutron star observation, which was GW 170817, actually ruled out several of the Horndeski models that I talked earlier, because they predict speed of light to be not equal to speed of gravitational waves. And for example, one of the most important alternative theory which has been used for a long time would be the scalar coupled Gauss-Bonnet gravity. So it turns out that in the cosmological scale, the scalar coupled Gauss-Bonnet gravity can actually be written in terms of Horndeski model. As a consequence, they are ruled out at least as a dark energy candidate. So therefore, since one observation can rule out so many models, so therefore one may wonder that what happens when future observations come in, and one hope that one should be able to talk more about constraining them and ruling out them in future. So I will just finish with future directions and question. So first of all, there was this nice paper by Professor Astekar and Ganesham Date, who is here, regarding the quadruple moment formula in de Sitter spacetime. So I have not heard of any development on that regarding the tidal love number, because tidal love number definition still works on asymptotically flat spacetime. And then what happens to the universality of this I love Q relation in the context of de Sitter? Even though this may not be of very interest to the recent GW detection, but I think at a theoretical perspective, these are of importance. Then in the post-Newtonian case, the effective one-body representation has been used quite routinely in the normal GW calculation, but the validity of that in beyond general relativity theories, I don't think has been explored, so that also one needs to think about. Finally, regarding the merger phase between the beyond GR theories, the main problem that lies is the well-posedness of the initial value problem. Because only for general relativity, the well-posedness, the initial value problem is well-posed. For other theories, like for example in Horndeski kind of theories, there have been some work by Harvey Rial, which showed that if you consider the just Horndeski theories in the harmonic gauge, then it's not strongly hyperbolic, the evolution equation. But that does not tell that it's not well-posed, because there could be some other gauge where they are globally or strongly hyperbolic. So this remains an open question, that which of the theories beyond GR has a well-posed initial value problem. Then of course there are the degeneracy issues, like whether there could be degeneracy between equation of state of a neutron star and some theories beyond GR. So how could you tell that it's a theory beyond GR or it's some different equation of state? Possibly the I love Q relation will help us in that manner, because we know that in the context of theories beyond GR, many of them will actually lead to a universal relation for the equation of state. So maybe that can be used to break the degeneracy. Then there could be some, again, distinguishing feature is needed between the gravity theories beyond GR as well as black hole mimickers, because they can also lead to some very similar results. So I guess some, thought in this direction, as well as the idea about the well-posed initial value problem is needed to go beyond this stage. But I hope it should be a good exercise to look into the future, and future GW detectors will help us to constrain or even rule out these theories. So thank you very much.
Questions?
So these the tidal low numbers of black holes in some of the alternative theories. So are you saying that there is a minimum tidal low number below which the black holes are unstable in these theories?
So
like neutron stars or something?
No, the love numbers in this particular black hole case, they can be either positive or negative, and their values are pretty less, like maybe 0.5 and 1. So therefore, I think they will most.
Can they be zero as well?
They cannot be zero generically, because the way it comes, if this parameter is even non-zero, however tiny it is, that will always predict a non-zero value.
Thanks.
So regarding your third point here, I'd like to comment. I think when we add those additional terms into the action, the resulting equation of motion may not have well-posed initial value problems, but people thought that these are due to the fact that these are effective theories which are only valid at low curvature.
Yes.
So I want to raise, there are this recent work by Masha Okonkova and Leo Stein. So they were taking a different approach. Instead of trying to solve these equations directly, what they do is they treat these additional terms in the action as perturbations. And then they did a perturbation on top of the numerical spacetimes obtained from binary black hole merger. And then these perturbations are linear perturbations, which are sourced by the higher terms. And therefore, I think it's a very interesting approach, because, of course, this is not exactly solving those equations, but they're solving the equation at a linear order in the small quantities in front of these terms. And also, they're able to obtain the full in-spiral merger ring-down waveform. I think that's a very interesting step toward the test of GR.
Perturbatively, but what about the dynamical equations?
Oh, they did the whole thing. They did the whole space-time evolution. So these source terms are time-dependent source terms in their linearized Einstein's equations, which are on the dynamical space-time as a background. So in that sense, they did get the full waveform.
Initial slides, you said something about you need second-order equations to avoid the Ostrogatsky ghost,
Yes.
right? Is that a like a necessary condition? I don't think, because FFR theories have, like, if you don't have Arminian terms or something,
Sure.
just,
So the point is, I mean, in most of the cases, if you have fourth order equation, that will lead to the Ostrogatsky ghost. But in case of FFR and some other theories, you can actually have certain parameter space where that ghost is not present. So,
I think if you avoid curvature, if you just have curvature scalars or higher orders of curvature scalars,
Yes.
you anyway avoid the ghost condition, I guess.
we essentially need this mass to be positive, the effective mass and
Sure.
so on. So for certain parameter space, it can be avoided, yes.
I wonder about the environmental effects. If they have this, Jan Bay and I were at some conference last week, and they were mentioning if the binary is made in the presence of the close to a supermassive black hole or intermediate mass black hole or has a large kick, then when we make the estimate, this is a question for the whole panel. When we make this estimate of the beyond GR parameters, then we will have a systematic bias or sort of excess noise, which comes from the fact that we don't know the environment of the binary. And then that can give us a thing which is outside of the usual manifold and look like a beyond GR effect. And how are we supposed to take this into account and place upper limits? It seems like this is always an unknown variable because we don't know really where it comes from.
Forget about the environment of the binary. We don't understand well the detector itself. So, actually, we are. I think the LVC collaboration, especially the test of GR group, is more or less aware of the fact that we're going to see, some evidence of non-GR things in the upcoming detector in runs, and we will have to really invest a lot of time characterizing systematics due to the fact that we do not understand all the detector systematics as well as the waveform systematics. But then the environmental effects would come the next level.
No, I don't think this is right. I think if you look into the next several years, we will have the detector calibration down to the 0.2% level. And at that point, then the environmental effects become the limit. But it seems to me like technologically, we can always push the detector calibration below the 0.1% level, but there's nothing that we can do to control the environment that the binaries are generated in. So maybe this, there is some
half answer would be
population synthesis people around who can say, given 10,000 binaries, what fraction of them would be limited by these biasing effects?
So Rana, so you're right. But if we observe multiple these supermassive binary black holes in LISA or whatever, and if their environments are uncorrelated, then perhaps there won't be a systematic bias all in one direction from these multiple observations. But on the other hand, yeah, they actually may be correlated. So in that case, that will set some limits on how well these things can be tested.
No, I think it's always in the correlated sense, because if it's generated in the dense environment, then the signal is always coming from inside of the gravity well. It's never coming from the anti-gravity well. So there's a bias in one direction.
The system got kicked out.
Just wanted to comment that, Rana, in the same way you are improving the detector, people are computing in a quantitative way the effect due to the environment. So there are papers where people have formula that predict these effects, and some of them come up as higher order post-Newtonian terms, for example. So I would say that people are doing the work to predicting also these terms, and I'm not particularly worried in the same way you are not worried about the detectors.
Maybe can I comment one more? I think if it's a deviation of GR, it has to be some kind of persistent, and also has to be, I think like Rana said, if the environment have persistent trends, also Sumanta said, right? when we look for these deviations from GR, they have to have a particular dependence. These deviations have to have a particular dependence on the parameters. For example, when Chris was showing these PN coefficient deviations, I actually had the question, right? We're stacking together all these coefficients and get a more narrow plot. But what if for different binaries, the deviation from GR may be different, right? So we should think about these issues. Like we should look for features that are for all the sources that have common, and then they stack together, they add up in a way that shows that there's a persistent trend in the deviation. And then we can say, oh, we found something. Then it may be due to GR or due to environment, but we need to look for this.
Yes, I agree, of course, but a quick comment on that. Even if you have a GR violation that doesn't cause a deviation always in one direction, it could alternate, it doesn't matter, then you can look at log base factors. And that is going to build up.
Right, I agree. So yeah, but the ones that go one way would accumulate faster than the things that go the other way, where
yes,
it accumulates.
The evidence would accumulate faster, probably.
Yes.
But that is even true.
Talk later. So yeah, so you're welcome to make comments on all the talks today, also including Badri's talk, because he's still online.
We have come up with maybe a dozen of different ways of testing general relativity. They all test different features. At some point, I think it would be useful to classify them that they are testing essentially the same thing. I'll give you an example. For instance, testing the post-Newtonian structure could be formulated as testing maybe the multipole structure of the space-time itself. So in this manner, I think it would be useful to have a classification. Cosmologists did this after nearly 20 years. They wrote down what is it that we are testing between, using all these phenomenological different ways. Do you think what we are doing is amenable to such a thing? This is just a general question for the panel, so that we can minimize the number of things that we do and not increase the trials factor, as it were.
Yeah, I think it is the case that the various results that we put out there often actually come from the same kind of measurement, right? For instance, the modified gravitational wave propagation can be mapped onto, right? Sorry? Oh. Yeah, is this better? Okay, thank you. So what I was saying was, it is of course true that, for instance, anomalous gravitational wave propagation can be mapped onto a PN coefficient to leading order at least. So it is, in that sense, the same test. It is just that we are drawing different conclusions from that basic test at a different, we're trying to get different kind of information, but at the operational level, it is the same test. That is true.
The number of tests that we are doing, the smallest test, so that it will have the greatest impact, is what I'm saying. Maybe that requires some amount of work to say, for instance, polarization is qualitatively different from everything else, and therefore that could be very valuable. Whereas the different post-Newtonian tests that we do, in spiral mergering down or just post-Newtonian coefficients, those are probably similar to also propagation effects. Maybe there are elements in propagation effects that are not captured by post-Newtonian theory. I think it requires some thought, right, as to which are really the independent tests that we want to perform.
Yeah, I agree. For instance, yeah, in the case of propagation, if you have if it's not a massive graviton, where we already knew beforehand that the Compton wavelength of the graviton would be way larger than the size of the system, and therefore probably no effect from dynamics, then it's fine. But you have to think a little deeper if you are looking for an effect or something that has an effect on propagation and dynamics.
But I think propagation dynamics is a little bit different in the sense that the propagation effect, the phase shift you accumulate depend on the distance of the source. But for the dynamics itself, the effects are independent. So in that sense, they're different.
Physically, they are different. Sometimes they're captured by a modification in the post-Newtonian. I mean, this is the way Cliff Will formulated it in the first place. But then physically, they are different. But the question is, what does get modified in the waveform?
So you're saying from the source, from the data point of view, you make a few products, like the deviation in phase, and then the other people will use this to apply on the different theories.
Yeah, you can interpret differently, but all we need to do is just one set of things, and
yeah, that I agree.
I mean, if there is time, can we go back to what Abhay was asking, or are there other questions that you want to ask? Yeah.
So Chris, maybe we should show your slide.
Yeah. Because I was under the impression that the post-Newtonian theory still uses, especially for binary neutron stars, for a long time we have agreed or understood that it is not necessary to worry about the full in-spiral mergering down waveform for binary neutron stars. So there it's really the post-Newtonian theory that we're still using.
Actually, I wonder whether post-Newtonian people or Alessandra can pitch in on this.
Yeah.
We have a post-Newtonian.
So what we are doing really is that these are really post-Newtonian coefficients. And we are trying to measure deviation by using the in-spiral part of the signal. Would you trust that, no matter what, up to how many terms we compute, those post-Newtonian coefficients remain the same. But what Abhay is saying is, if you don't know the higher order post-Newtonian, it modifies an earlier coefficient. Is that correct?
They look like a modification.
Look like a modification. Yeah. And so this may not capture test of GR in some sense.
Or the failure is not failure of GR.
First, those coefficients, they depend on a lot of assumptions, and not assumptions, but properties of the system we are studying, and also properties of GR, like they are what they are because there is some effacement principle, there is some weak and strong equivalence principle, and so on. When you compute them, you see how the different assumptions or properties of the theory will make them what they are. Second, we know nothing or very little about this asymptotic post-Newtonian series. We don't know if it is convergent and if it's a real series, and we observe actually that it is not very well behaved for the low order we know now. I'm not sure a higher order coefficient which is unknown could mimic or modify, if we don't know it, could bias, let's say, the values of former coefficients. It's not obvious because
No, they won't modify. No, that I agree. They won't modify the earlier terms.
Can I say one thing?
Okay. Well, yeah.
Did you finish?
Yeah, so you can say something.
Okay. So I'm not completely sure that I understood your question. But if I understood your question, what you are saying is, for example, if we were doing an exercise where you inject a GR signal, instead of using the data, you just inject in the data a GR signal from a numerical simulation, you might see a spurious GR deviation in that case. Okay, this is what you are saying. If there is this problem with the coefficient not, that the coefficient are not converging, but this is not happening. We do injections of NR signals, and we see exactly what you see in that plot. And the reason is because this waveform, I think Chris was saying this, the waveform is already calibrated to a GR. So the higher order terms in these waveforms, which we don't know in PN, have been fitted to GR. So if you want, you start from a waveform which is very close to GR, and then you are just allowing these parameters, including the one predicted in PN, to change with respect to the GR value. So your worry would be there if we were not at all, calibrating the waveform to GR and using, for example, something that we have no idea whether it's close to general relativity or not. But this is not what we are doing here. The injection, yeah, I mean, because we have done this study to understand whether the test makes sense. Otherwise, we would not have. And also, the last thing I wanted to say is that just also to pay attention to the fact that we are doing a test of GR, but this is not a very stringent test, because if you take the binary neutron star result, you have at -1 PN, even 2 orders of magnitude better than you see in this plot. But when you ask the question, how much the dipole radiation is really constrained, and you take, Brans-Dicke theory, omega Brans-Dicke is larger than 1. And we know that it's larger than 40,000 from the Cassini. So just to give an idea, I mean, I'm not saying that this is bad, but I want to give you an idea that although for the first time we are bounding these parameters, we are not, there is still a lot of room there of variation with respect of general relativity. I mean, even if you see 10% or 10 to the -3, okay, that's also to keep in mind. We are not very stringently yet.
Can I quickly,
but not,
though it's a different point, can I quickly comment on that? Yeah. I would not get fixated on -1 PN. To me, -1 PN is not interesting. Sure,
to give
to
an
other
idea,
types of measurement.
Theory that people know.
no, but it's the higher order.
To other types of measurement, but who can constrain this? Who else other than we can constrain this?
But I wanted to say, if you translate these constraints on something that people are familiar with, in terms of specific theory, that's the one example you can keep in mind.
That is correct, but those other measurements cannot test the higher order terms.
Okay,
You know that.
And even at -1 PN, you can have late time scalarization.
Okay, we have.
Sorry, I have a question maybe for you. Isn't it possible, so I understand that you calibrate, for instance, adding some 5 PN unknown effect, but you know it's here and you fit this to numerical relativity. But when you know it, maybe it will be different from what you expect. And this means that the calibration was just a way to fit with numerical relativity, and maybe in fact the good thing to do would have been to include the 6 PN coefficient, or I don't know. So it's possible that's still possible that in spite of the calibration there are problems. Maybe I play the devil here, but
So first of all, in fact, I can tell you already now that if tomorrow you compute the 5 PN term, it's not going to agree with the 5 PN coefficient that we have put in the potential, for example, in the effective one-body description, because we are calibrating the waveforms, and the waveform have also dissipative, effects. So we are putting all our ignorance in one term in the potential, but that term is taking into account, for example, we don't put absorption terms that are also there, So I'm not saying that the terms that we fit would agree with PN when you compute them. In fact, it's important that you continue to compute these terms at higher orders, because we will improve the waveform, the underlying waveform, more and more, and pushing these, disagreements at higher and higher order. So on this, I agree with you, if this was your question. It's still important to get the post-Newtonian terms at higher orders.
I think we should finish the session. We are already 5 minutes. Oh, but Bala needs to say something. You get the final question. Last word.
Yeah, no, Abhay's worries, comes from the fact that the post-Newtonian expansion is asymptotic. But I think we can take a lesson from the post-Newtonian expansion in the test particle limit, where, for example, when they were doing the self-force kind of calculation, right? For example, Ryushi's thing said that we know the coefficient up to 22 pn. Now, when you look at those results, for example, the kind of results, for example, which Shah did, where you really compute numerically to some 120 places of decimal, something, and then you try to fit it to post-Newtonian kind of coefficients, it is not as bad as one thinks out. For example, Nathan can probably comment on this. So the higher order coefficients are not so asymptotically, what you call, so bad that they will spoil our physical intuition of what we expect to happen. Right? Because I thought, when you... Yeah, no, but but I'm just saying that the fact that when we cannot sort of dismiss the match with the numerical thing, and so the fact that we don't, I'm not just talking about the measurement, I'm just talking about the post-Newtonian series itself, and the fact that what you can do analytically and what you can do numerically, their consistency should not be dismissed. And when you look at that pattern, it does not really sort of say that there is really room to worry about the, technically what you're saying, which should be there, but we cannot dismiss what we know about the post-Newtonian expansion in the test particle limit.
I'm not taking anything away. I'm not dismissing anything, but I'm just saying that if you want to come and say that in fact there is actually a violation of general relativity, or then I think I would really like what Satya said. Then I would like to revisit the whole thing. I mean, I think we should do it in the coffee break, because I think I'm not quite happy with the answers that were given, and maybe I'm missing something. So I'd like to understand.
So let's thank all the speakers for the session.